Welcome to the Explainer. Today we're going to get right into it and do a deep technical dive into WireGuard. It's the VPN protocol that everyone's talking about because of its speed, its simplicity, and its really modern approach to security. We're going to pull back the curtain and really see what makes this thing tick. But let's kick things off with a question that really gets to the core of why WireGuard even exists. What if all that complexity you see in other VPNs wasn't a feature, but actually a bug? What if you could build a VPN from scratch to be minimal, ridiculously fast, and secure right out of the box, not hours of configuration? Well, that's the promise we're going to explore today. So, here's our game plan for this explainer. We're starting with the fundamental design ideas, then we'll get into how it handles identity with keys. After that, we're going to follow a single packet on its journey, unpack the real magic behind something called crypto key routing, and then we'll put it all together in a practical example you can actually use.
Okay, let's jump right in. To really get WireGuard, you have to start with its core principles. This isn't just some other VPN protocol. It's a fundamentally different way of thinking about how to build a secure network.
And what's so brilliant here is how all of these principles just feed into each other. Take simplicity. The entire code base is only about 4,000 lines of code. That is tiny. It means you can actually audit it, which seriously cuts down on security bugs. This focus on being lean also allows for incredible performance, which gets another huge boost because it runs right inside the Linux kernel. It all just clicks together.
Now, this concept is absolutely crucial. WireGuard is what we call opinionated about its cryptography. You know how older VPNs give you this giant menu of encryption algorithms to choose from, and some of them might be old or weak? Well, WireGuard just doesn't do that. It picks one modern, super fast, and heavily vetted set of tools for you. By taking away that choice, it completely eliminates a whole category of security problems that come from people just picking the wrong settings.
Okay, so that brings us to the very foundation of WireGuard's security model. It all boils down to a really elegant and simple system of keys and peers. This is how the tunnel figures out who is who and who to trust.
If you've ever set up SSH, this is going to feel second nature. Every single device, or peer, as WireGuard calls it, gets a key pair. You have your private key. That's your secret. It never, ever leaves your machine. It's what proves you are who you say you are. Then you have the public key. Think of it like your phone number or your email address. You hand it out to any peer you want to connect with, so they can verify it's really you talking to them.
And making these keys, it's just as simple as the idea itself. Seriously, on any machine you want to put on the VPN, you just run two little commands. First, wg-gen-key spits out your secret private key. Then you use wg-pub-key to generate the matching public key you can share. That's it. You're done.
All right, now we get to the really cool part. Let's actually follow a single packet of data on its journey through the WireGuard tunnel. If you can wrap your head around this flow, you'll understand exactly how WireGuard pulls off being so secure and so fast at the same time.
Okay, so picture this. A regular unencrypted data packet shows up at the virtual WireGuard network interface. The first thing WireGuard does is look at where that packet is trying to go, its destination IP, and asks a simple question. Do I have a peer configured for this address? If the answer is no, that packet is just dropped, gone. But if it finds a match, it grabs that peer's public key, encrypts the data, slaps on a tiny WireGuard header, and fires it off over UDP. And using UDP is a big deal. It's way faster for things like voice and video because it skips all the extra overhead.
Now, what happens on the receiving end is just as slick and just as strict. A packet comes in from the internet. WireGuard tries to authenticate and decrypt it. If anything fails, anything at all, the packet is silently dropped. No error message gets sent back, which makes WireGuard really stealthy on the network. If it succeeds, it does something really clever. It updates the sender's public IP address. This is the secret sauce that lets you switch from Wi-Fi to your cell network without the VPN ever disconnecting. It just roams with you. But it's not done. It does one final critical check. Does the source IP from inside the now decrypted packet actually match what I'm allowed to receive from this peer? Only if it passes every single one of those checks does the packet finally get handed off to your computer. So remember that final check we just talked about, the allowed IPs list? Well, that is the key to one of WireGuard's most brilliant ideas, something called crypto key routing. Let's dig into how this one simple setting is doing two jobs at once.
The absolute beauty of this system is that the allowed IP setting is basically a two-for-one deal. When you're sending traffic out, it acts like a routing table. It says, hey, if a packet is trying to get to one of these IPs, you need to encrypt it with this specific peer's public key. But for traffic coming in, it acts like a firewall. It says, I just decrypted a packet from this peer, and I will only accept it if its source IP is on this specific list. It creates this unbreakable bond between a cryptographic key and a set of IP addresses. That's the whole magic of crypto key routing.
All right, that's enough theory. Let's make this real. We're going to walk through one of the most common uses for a VPN, securely connecting a small branch office back to the main head office. We'll build a site-to-site VPN with WireGuard, step by step.
Okay, so here are the vitals for our two locations. We've got their public IPs, their addresses on the real internet. We have the private tunnel addresses they're going to use to talk to each other inside the VPN. They'll both listen on the standard WireGuard port. And most importantly, we have the local office networks, the LAN subnets that we want to connect together. We're going to use these exact numbers to build our config files.
And here it is. This is the config for the branch office, and you can see that crypto key routing we just talked about live in action. The interface section is all about itself, its private tunnel IP, and its own secret key. Then the peer section is all about the head office. And look at that crucial allowed IPs line. It's telling the branch office two things. First, route any traffic meant for the head office's entire network to this peer. And second, only accept traffic from this peer if it actually comes from that network.
And here's the other side of the coin, the head office config. It's basically a mirror image, right? It defines its own interface and its own private key. And in the peer section, it lists the branch office's public key and its allowed IPs, which are the branch office's local network, and its tunnel IP. But see that one extra line, endpoint? That's how the head office knows the public internet address of the branch office, so it knows where to send packets if it needs to start the conversation. And just like that, with two really simple text files, we've built a rock-solid, secure tunnel connecting two entire office networks.
So we've seen it all come together. The tiny codebase, the opinionated crypto, that incredibly clever design of crypto key routing. It's just powerful but so simple. And that leaves us with one last big question to think about. Is this minimalist, secure by default approach more than just a better VPN? Could it actually be a blueprint for how we should be building all of our secure network tools from now on? It is definitely a compelling thought.